Good morning. This is a video lecture on dynamics. So to get the bigger picture, so we have here physics or top our subject, and we have mechanics as the sub or the branch of physics, and then under mechanics we have kinematics, dynamics, and statistical mechanics. So dynamics is again causes of motion. So it's a branch of physics. It's a branch of physics developed in classical mechanics concerned with the study of forces and their effects on motion. So this is the study of forces, which is the causes of motion, or why do objects move. So what makes an object move is because of these forces. And then what is a force? So a force is just a push or a pull. So a push, so if you are pushing something, you are exerting a force on something. And if you are pulling on something, then you are exerting a force on that something. So we have three laws of motion. We have the law of inertia, the law of acceleration, and the law of interaction. So these three laws were formulated by Isaac Newton, although some of these ideas come from Galileo Galilei. So he was able to he was the first to study the details of motion, or the details of motion, and he was able to come up with these three laws. So let's start with Newton's third law of motion. According to Isaac Newton, that for every action there is always equal and opposite reaction. So for every force that is acted, there is equal and opposite force that is also acting on the object. So for every opposite force, we have to write negative to indicate that this one is an opposite force. So both forces are acting on the opposite direction. So if one is acting to the right, the other opposite reaction force is to the left, or either ways. And then you could also have it or say it this way: for every push, there is always equal and opposite push. Again, this push here has a negative symbol to indicate that that is in the opposite direction. So say you have here, you have your forefinger. So let us say your left forefinger is pushing your right forefinger, such that your right forefinger remains still. So as you push your right forefinger, the harder you push your right forefinger, the the more difficult that your left forefinger would feel. Again, provided that your right forefinger remain still. So the less force you exert, the less force, or the less push you give, the less resistance you would also get, or the less resistance your left forefinger would feel. The harder you push, the more difficult, or your left forefinger would experience more difficulty in pushing your right forefinger. So again, these forces exist in pairs, so one cannot exist without the other. So you cannot say that you are pushing the other forefinger, and then your right forefinger would not feel force at all. So a force exists if the other one also feels the force exerted by the other one. So they come in first. It's like you're pushing the wall. The harder you push the wall, the harder also you would feel that the wall is pushing you. I mean, the less harder you push, the less harder also you feel that you're pushing the wall. So you could also, that is the force of the right forefinger on your left forefinger. You could also say it this way: you cannot touch something unless you are touched. So you cannot touch someone's face unless unless that face touches your palm. So you cannot push something unless that something is pushing also you also. So if this little girl kicks the ball to that direction, so the force of foot on the ball, so this is how to name forces. So force of what on what? So force of foot on ball. The same way as the ball also is pushing the foot to the other direction. So that is force of ball on foot. So between the box and the table, I will do the first one. This is the force of the box on the table. So it's like the box is pushing the table down because of gravity. So since the table is carrying the box, so the table feels the push of gravity on from the box on him, on the table top. And then in return, the table also is pushing the box to the opposite direction. Again, these forces are pair forces. One cannot exist without the other, and these forces also cannot cancel out because they are acting on different objects. So you can see it from here. The force is acting on the box, and this force is acting on the table. So you cannot cancel them out because they are acting on different objects. So law of interaction can be felt or can be really seen in this situation. So the bullet is being pushed by the gun outside the barrel. In return, the bullet is also pushing the gun along with the person holding the gun to the opposite direction. So that's why you could see that the girl was moved to the opposite direction. So again, the bullet is being pushed to the right, then the gun along with the person was being pushed to the left. Now, Newton's first law of motion. So an object at rest tends to remain at rest. An object in motion tends to be in motion at a constant velocity unless acted by an outside force. So let's have the first one. An object at rest tends to remain at rest. So an object placed on a certain location, unless someone pushes it, it will not move. Unless something has pushed that object, it will not move. It will not move forever because there is no net force, there is no outside force acting on the object. So it will remain at rest, it will remain still. And an object in motion, so let us say I have here an object, a ball rolling down an inclined plane wherein the track is very smooth such that friction is zero. So we have here an incline, and on this portion right there, it already becomes flat. So this is a flat, smooth surface. And then you have here an incline at the first previous part. So let us say this metal ball or this ball is released from IAU campus and such that we are able to create a track up to SMC side. Question is, will the ball reach SMC side if again the surface is very smooth such that friction is zero? Do you think it will reach SMC side? So let us say SMC side is around 10 to 15 kilometers from IAU campus. So will it be able to reach SMC side? And let us say the ball is released, let us say 1 meter above the ground. So with 1 meter above the ground, will it be able to reach SMC side? Just that the surface is very smooth, no air in this situation, no air present. And what about if we exaggerate the situation, that we will be able to create a track from IAU and then connect it along with the seas and lands such that it now circles the earth? Question is, will the ball released at a height of 1 meter from an inclined plane to a flat surface be able to reach or circle around the earth such that again there is no air resistance, the surface is very smooth and continuous? Now there is one object that is doing it many years ago already, since its existence. So we have the moon that has been moving around the earth since the day it existed. So the answer to this question now is, will the ball be able to circle around the earth? Yes. And the answer to this question right here, will the ball reach SMC side? The answer is yes. According to Newton's laws of motion, an object at rest tends to remain at rest, and an object in motion tends to be in motion at a constant velocity unless a friction, an air resistance, or an outside force would slow it down until it stops. So provided that there is no outside force, this object will reach SMC side, this ball here will circle around the earth, and this moon, or the moon that has been circling around earth since the day it existed and up until now. So again, an object in motion tends to be in motion, constant velocity, unless acted by an outside force. So an object at rest tends to remain at rest unless acted by an outside force. So to say this object okay. So let us identify the pair forces that existed in this scenario situation. Between the box and the table, there are two pair forces. So force of the table and the force of the box on the table. Now, if we include Earth, so these are the pair the pair force. So we have more than one pair forces that exist in this scenario. So if we include the Earth, because this thing is on Earth, and the Earth is pulling because of gravity, there's the force of Earth on the box. So the box is being pulled by the Earth downward. In return, the box also is pulling the Earth upward. Again, this force cannot exist without the other force. So these are pair forces. Now, so this is Newton's third law of motion about pair forces. So this is Newton's, we are not talking about law of inertia. So let us now focus on the forces acting on the box. Acting on the box. Acting on the box. So this one is on the table and this one is on Earth. So there are now two forces acting on the box. The force of the table on the box and the force of Earth on the box. So to rewrite that one, we have here the force on the table on the box, which is called normal force. What is a normal force? A normal force is a force perpendicular to the surface. So if this is your surface, this surface is exerting a force perpendicular to the surface. So that is when we say perpendicular at 90 degrees to the surface. And then we have here the force of gravity that is pushing the box downward. Now, since they both exert on the same item, on the same object, these forces cancels out. And in this case, net force is zero, meaning to say the forces acting on the object seems to have no effect on the box, seems to have been cancelled out. And that's the force, the net force is zero. Now, if net force is zero, there are two things that will happen. The object will not be moving at all, or the object will be moving, but it is at constant velocity, because a force is equal to mass times acceleration. If there is no net force, then there is no acceleration. If there is no acceleration, that you would expect that the velocity is constant. So let us now identify the forces acting on this scenario. So we have the force on Earth on ball, or the force of gravity, and we have the normal force that is perpendicular to the surface. The surface is this one, that one, that is perpendicular or not at 90 degrees. So the resultant of these two forces causes the object or the ball to move to that direction. So that is how we determine the resultant using parallelogram method. So the resultant is this force right here. So there is now a net force. Now, since there is a net force, you would expect that the object will accelerate. And then, as it accelerates downward, so once it started moving on a flat surface, the forces now acting on the object will be this one. Still, the force of the surface on the ball, or the normal force, and the force of gravity. But this time, the resultant of the two forces is zero, or the forces seems to cancel out. So let us say at this point right here, the ball now was able to reach at a velocity of 10 meters per second. Now, since it is already on a flat surface, and you know and you have seen it that there is no net force here is zero, that means that the ball will continue to roll to that direction at 10 meters per second unless there is some sort of friction or air resistance that is trying to slow down the ball. But since our situation right here is that it is very smooth, friction is zero, air resistance is zero, so the velocity here will be constant. So the object will be moving at constant velocity of 10 meters per second forever unless there is a barrier along the way that would tend to stop the ball. Now let us now draw free body diagrams. What is a free body diagram? Free body diagram is a diagram or a set of drawing of forces or arrows, or forces represented by arrows that is acting on the object. So everything or all forces is acting on the object. So we have here the object, which is a rock, which is hanging on the air and is somehow being pulled by this string right here and this string right here. So we don't forget gravity is also pulling the object downward. And we have here, we call that one tension 1 or T1, and this one is tension 2. So these are the forces. When we say tension, it's a force that tends to pull a string or stretch a string. So as the string is pulling the object, so it could feel somewhat stretch on its gun. It's like yeah, it's like it's being stretched as it pulls this rock. So we call that one tension. But question now is, how long should the forces be? So how do we know that it should be of this length, should be of this magnitude? So using parallelogram method, we will be able to know how long should the other forces be, or how long should, yes, the other forces be. So first you draw force of gravity. So you may draw it maybe a little shorter or a little longer, that's still correct, as long as you have your force of gravity. Now the other forces will now be proportional to the force of gravity. So how do we know its proportion? So the next thing you're going to do is to draw a line parallel, no, not parallel, a mirror image of the force of gravity. Meaning to say, that should be of the same length as the force of gravity. After that, you draw a line marking the end of the mirror line. Okay, so that is the end of the mirror line. And from that, your force of the string should be up to that position right there. So that should be at that mark. So by then we know that tension 1 should be that long. So looking at the proportions, you would see that tension 1 is greater compared to force of gravity. So meaning to say, the string is pulling the rock more than its weight. And then how do we draw tension 2? So you draw a line parallel to tension 1 and you put it here. So by that this point right here is the end point of your tension 2. So that is now of correct proportion. So since we already we've been mentioning that the forces cancels out if the object is not moving. So which forces cancels out? Now the resultant of tension 1 and tension 2 is this line right here. So we know that one from our parallelogram method. So this is the resultant. So if you combine T1 and T2, this is the resultant. And this resultant is being cancelled out by gravity. So meaning to say, the whole thing, the forces cancels out. So we have three forces that exist in this scenario. We have the force of gravity, tension 1, and tension 2. So to recall, we have here our drawing, in which the lengths, the magnitudes are not of correct proportion. And by using parallelogram method, we were able to know the correct proportions of the arrows. So there is a line here. This is a line parallel to tension 1. So there are three forces that exist, tension 1, tension 2, and force of gravity. And this is now of correct proportion, wherein tension 1 is exerting more than the weight of the object, and tension 2 is only exerting a little. We have here another situation. So we have here a rock on an incline that is not sliding. So friction prevents it from sliding. So we have here force of gravity. So again, draw first force of gravity, and the length of which is not really important, but that length is proportional to the other force, the length of the other forces. So a mirror image of that force, and then you draw a line parallel to the surface, so that where your normal force ends to that position there. And then now, if there was no friction, you would expect that the object will move downward, because the resultant of Fn, or the normal force and gravity, is this one right here. So there is a resultant force. So to know the length, or the length of your friction force, should be you draw a line parallel to the normal force, and then put it at the end of the mirror image, and then that is where your friction force ends. So that is how long your friction force should be. Now, do we have to draw the net force? No, because that is not an actual force. That is only the result of force, normal, and force of gravity. So this is now an actual force, a friction force. You follow? Meaning to say, the resultant of friction, normal force, and force of gravity is cancelled out by friction force. Okay, so again, to do it again, so we have force of gravity, then you draw a line parallel, mirror image of the force of gravity, then you draw a line parallel to the surface, then that is where force, normal force ends. And since this one is not sliding, or is not moving downward to this downward direction, there must have been a friction that prevents it from moving to the opposite direction, and that is the amount of friction force you have. Newton's second law of motion is, or states, that if there is a presence of a net force, or if there is net force acting on an object, or the net force acting on an object causes an object to accelerate. So if there is a net force acting on a mass, on a certain mass, or on a certain object having mass, then that object should accelerate. And in this case, there is no net force. Net force is 0, so therefore this object will not accelerate, so it will only move at constant velocity. Whereas this one right here, we have here increasing velocity, so that means there is acceleration, so you would expect that there is a net force exerting on this object right here. So moving on, or going further, so let us say you have this mass of object, and you want this object to accelerate to that direction, so you need to exert a force. Say you want it to accelerate more, you want it to move faster. or you want it to move farther, so you need to exert more force so that it will accelerate more. Okay, so this is just a very simple equations. This is just showing you the relationship that when uh, when there is an increase in acceleration, that means it was applied by a greater force. Or as acceleration increases, force increases, or as force increases, then the object will accelerate more. And say you have this wagon with an object or a mass placed on it. So if you are exerting a force on this wagon, the wagon will accelerate. Now say the amount of object in a wagon was increased 4 times. So the mass increases. There are two things that will happen here. First, you can pull it at the same amount of force, and then the mass what was increased 4 times. So you would expect that the acceleration will decrease 4 times. And then the other situation is you would want it to move at the same rate, at the same acceleration, meaning you will have to move together with the other one at the same rate. So you need to, so again, we're in that, the mass of this example right here was increased to 4 times compared to the other one. So you need to exert a greater force so that you would accelerate the object at the same rate as with this one. So that they will be moving together at the same rate, you need to exert a greater force because you have greater mass in it. Now, this was conducted on the moon. I think it was Apollo 15. I'm not really sure. A hammer and a feather was dropped or released, and they were able to find out that they reaches the ground at the same time. Meaning to say, if they reaches the ground at the same time, they have the same amount of acceleration. And Galileo was also doing that one, a lighter object and a heavier object dropped the Leaning Tower of Pisa, and he was able to find out, I think that was during 1600s, that a lighter ball and a heavy ball will reach the ground at the same time if they are released at the same time. So regardless of mass, all objects on Earth will accelerate at 9.8 meters per second squared. And all objects on the moon will accelerate at around 1.6 meters per second squared. So what happens to this one in terms of our equation? So since our feather has a small mass and at this certain acceleration, so it has this amount of force of gravity. And since our hammer is heavier, therefore it has greater force of gravity, but then again they have the same acceleration. So what differs is their force of gravity. Hammer has greater force of gravity compared to a feather, but they will reach the ground at the same time because they have the same rate of change of velocity, or they have the same acceleration. So free body diagram on second law of motion. So as you can see that the rock is sliding on a frictionless surface. So you could observe that the distance here, that is for every second, increases. So that means that the velocity increases, then acceleration, there is acceleration. So first identify the force of gravity, and then a mirror image of the force of gravity, and then you draw a line parallel to the surface. That is where your friction normal force ends, and the result of normal force and the force of gravity is the net force. And to draw the net force, you draw a line, you draw a mirror image of the normal force, and then move it to this end of the force of gravity, and that is how long your net force should be. So you see from here that your net force is less than the force of gravity. Meaning to say, if they have the same mass, then you would expect that this ball or this rock will accelerate at a lower or less than the acceleration due to gravity, which is 9.8 meters per second squared. So this is somehow half of force of gravity. So you would expect that this one will move at a rate of somehow 4.9 meters per second squared. So meaning to say, um, If there is no surface at all, there is no normal force, then the object will accelerate at 9.8 meters per second squared. That is if there is no surface. But since there is a surface, then your net force is less compared to the force of gravity. So to recall, Newton's law of inertia, net force is zero. There is no net force. But for Newton's second law of motion, there is net force already. So you would expect that there is acceleration because force is equal to mass times acceleration. So to do it again, so we have mirror image of force of gravity, then mirror image of force of gravity, and then a line parallel to the surface, and then your normal force ends there, and you draw a line mirror to the normal force, and that is where your net force ends. So this is the actual force. No, there are only two actual force. We have the Fn and the Fg. This one is just a resultant force. So that is just an apparent force. The actual force that exists is really the normal force and the force of gravity. So to recall, we have discussed Newton's third law of motions, the law of interaction, which states that for every action there is always equal and opposite reaction. So for every push there is equal and opposite push that is experienced by the one pushing. And Newton's first law of motion states that the law of inertia, an object at rest tends to remain at rest, and an object in motion tends to remain in motion unless acted by an outside force. And Newton's second law of motion, which states the law of acceleration, which states that if an object experiences a net force, that object will have to accelerate. And we also discussed free body diagramming, where we are able to draw or identify the forces acting on the object and somehow identify a resultant force. It could be a net force or it could be a net force is zero. So we are able to identify the forces using free body diagram. So that will be all. Thank you.